More examples for class 23. Here is, whoops, we already did this one. Just want to go to this one. There you go. A car uses an average power of 25 horsepower for 1 hour round trip with a thermal efficiency of 35%. How much fuel energy was used? What happened to all the energy? What change in entropy took place if we assume an ambient temperature of 20 degrees Celsius? Okay, well, let's walk through it. I like problems with cars. Car problems. I don't like having car problems, but I like these kinds of problems with cars. All right, so 25 horsepower. We had degrees Celsius. We're kind of like being mixed messages here. The US units, SI, US units, SI. Let's go with SI. So let's turn those 25 horsepower into kilowatts, and that conversion factor is 0.7457, and we end up getting 18.64 kilowatts. All right, so how much work does that represent? Well, you have power times time, or you had 18,640, no, not 18, 1,000, 18.64. These are kilojoules per second. And we have 3,600 seconds in an hour. So let's just put seconds. I don't have to do any conversions there. And we end up with 67,113 kilojoules. All right. And they said that it had an efficiency of 35%. Remember that the efficiency is what you want over what you paid for. So if you want this, you have to flip them around and go efficiency right there. It's the thermal efficiency, And so if you have 67,113 and you divide it by 0.35, you are going to get 191,750 kilojoules. Now, they didn't ask this, but I like real stuff. And so how much fuel is that? That is the amount of fuel energy that got put into the thing. Well, we're going to use gasoline, and we can look up, sometimes referred to as the higher heating value, or just a heating value, but you could look at Google heating value, or higher heating value also includes the water inside the fuel that turns into that. Don't worry about it. I looked up, there's a bunch of numbers. I got 49,000 kilojoules per kilogram. That's good enough for me. So I could find out what the mass flow is going to be of my 191,750 divided by 49,000. Then I'm going to get 3.913 kilograms. And I still don't know how much that is. But, because I don't know what a kilogram is. I mean, I don't have like a sense. I know what a 10-pound weight is, but I don't know what I can't get a sense what a kilogram is. But I know what a 2-liter bottle looks like. So let's get the density of gasoline. Being lazy and calling it gas, but 0.743 kilograms per liter is what I found somewhere for gasoline. So that means the volume that we would get would be 3.913 kilograms divided by 0.743, and I would end up with 5.27 liters. And now I have something that I could, and this thought bubble around there. Now I have something I get my head wrapped around. I know what a 2-liter bottle of Pepsi looks like, and so this would be like 2.5 and more and change of those 2 liters. Now I know how much gasoline they just burned. I can picture it at least. But going back up to the top, all they were really asking about was like how much entropy took place. Well, that's going to be delta S, and I don't know if this is a great question, but I liked the thing about the car. I don't know. We go Q over T, and it's going to be the outside temperature. All right, so this is going to be the environment, 191,750, and it went to 20 plus 273, because remember, we're going to get this, put those into there. So we have 654.4 kilojoules per degree Kelvin is how much entropy. And so where did this all go? Well, it all ended up, it ended up in the ambient. So one reason why we use this is because we went to that's the temperature that it ended up at, right? All that heat dissipated into the world as this entropy right there. I don't know. Was that problem worth it? This next problem's got a lot more to it, and then the next problem has a whole lot more to it. So this example, let's admit it, it's shit. But did it, so let's get credit for it and upload it, and then go to the next two examples, which much more difficult. See you soon.